Welcome back to Asteroid Day Live 2021. Thanks for sticking with us. I'm Lisa Burke, and in our final part of the programme, we're going to take a fascinating look into the future as we think about asteroids and the exploration of the solar system, both from a scientific and a commercial point of view. In the next 3 years, no fewer than 5 new missions will be launched to various different asteroids. Make no mistake, the asteroids are going to play a big role in our future exploration of space. And in this part, we're really going to open up our discussion to include the world of space resources and the development of technologies that will allow us to nurture an in-space economy. We'll be hearing about NASA's Psyche mission to a metal asteroid, NASA's Lucy mission to the Trojan asteroids, and JAXA's Martian Moons Exploration mission to what could be a captured asteroid in orbit around Mars. To start, here's Patrick Michel, Director of Research at CNRS and the Côte d'Azur Observatoire, who's here to tell us about the Near-Earth Object Modelling and Payloads for Protection, or NEO-MAPP project.
NEO-MAPP est en fait un projet financé par la Commission européenne. NEO-MAPP en fait veut dire modélisation des astéroïdes et instrumentation pour les missions spatiales vers les astéroïdes. C'est un acronyme anglais. Et en fait, il est composé de 15 laboratoires et industries qui ont pour but de faire des avancées très importantes sur plusieurs domaines liés à l'exploration et à la défense planétaire des astéroïdes. Donc la première chose, c'est qu'on veut augmenter nos possibilités de modéliser certains processus qui sont très importants pour comprendre les astéroïdes et aussi pour les dévier. En particulier, on veut pousser les simulations d'impact haute vitesse sur les astéroïdes, puisque l'un des projets est effectivement de dévier ces astéroïdes avec un impact haute vitesse, et ce sont des simulations très compliquées. On veut aussi pousser nos simulations de la dynamique des astéroïdes, en particulier certains astéroïdes sont doubles, comme notre petit système Terre-Lune, mais en petit. Et on veut pouvoir comprendre comment ces petits systèmes évoluent. Et puis, on veut aussi mieux modéliser leurs propriétés physiques et en particulier leur structure interne, parce que cette structure interne a une énorme influence sur leurs évolutions. Et en parallèle, on veut aussi pousser les développements instrumentaux pour les missions spatiales. On veut pouvoir embarquer des instruments qui nous permettent notamment de sonder la sous-surface par des radars, d'avoir une meilleure idée, une meilleure précision sur la forme de ces objets par des altimètres laser et des caméras, et puis aussi voir comment, quand ces objets vibrent lors d'un impact, les ondes sismiques se propagent, ce qui nous renseigne aussi sur leur structure interne. Donc, il y a tout un volet instrumentation. Et enfin, ces instruments font des mesures et il faut pouvoir les interpréter. Et donc, on veut revoir un petit peu comment est-ce qu'on analyse les données des missions spatiales en utilisant une approche multi-instrumentale, c'est-à-dire au lieu d'utiliser simplement les mesures d'un instrument pour augmenter nos connaissances, on veut combiner les mesures de tous les instruments pour pouvoir vraiment avoir encore de meilleures connaissances. Donc, en fait, c'est vraiment un projet qui a pour but d'améliorer non seulement nos connaissances des astéroïdes pour savoir comment les approcher et les dévier, et puis accompagner les missions spatiales avec des instruments et avec des analyses de données. Et ce projet vient du fait que d'abord la Commission européenne s'intéresse à la défense planétaire, comment se protéger des astéroïdes depuis un certain temps. Depuis 2012, elle a commencé à financer des consortiums européens pour pouvoir étudier ça. Et puis, nous, on a voulu, plusieurs d'entre nous, avancer, offrir nos compétences pour avancer ainsi, et bien sûr, avoir des moyens pour notamment recruter de jeunes chercheurs, les former pour qu'ils deviennent eux-mêmes experts dans ces domaines-là. Et pour avoir une référence pour ce projet, on a la mission HERA de l'Agence spatiale européenne qui, avec la mission DART de la NASA, va effectuer le premier test de déviation d'astéroïdes en utilisant justement un impacteur à haute vitesse. Et donc, finalement, notre projet accompagne le développement de cette mission. La plupart des membres de ce projet sont aussi membres de la mission HERA. Et donc, on va pouvoir accompagner ce développement, préparer finalement l'arrivée du satellite sur l'astéroïde et puis préparer aussi tous les outils qui vont nous permettre d'analyser les données. Donc, c'est absolument fascinant. Ça va permettre d'enrichir encore l'expertise déjà reconnue en Europe dans ces domaines et la transmettre aussi aux jeunes générations.
Hera is going to show us things no one's ever seen before. This ESA mission will be humanity's first ever spacecraft to visit a double asteroid, Didymos. This asteroid is typical of the thousands that pose an impact risk to our planet. Imagine a mountain in the sky with another rock about the size of the Great Pyramid swinging around it. That's Didymos. And just the seemingly tiny moon would be big enough to destroy a city if it were to collide with the Earth. But we're going to find out if it's possible to deflect it. This is going to be really, really hard. Aiming at a 160-meter wide target across millions of kilometers of void. Could we stop an asteroid hitting planet Earth? The dinosaurs couldn't, but we humans have the benefit of knowledge and science on our side. Hera is led by a multinational team of scientists and engineers, humanity's makers and doers. Right now, all we have is many years of research and theories, but Hera will revolutionize our understanding of asteroids and how to protect ourselves from them. First, NASA will slam its DART spacecraft into the smaller asteroid at more than 6 kilometers a second. Then ESA comes in. Hera will map the impact crater left by DART and measure the asteroid's mass. Knowing this mass is key to determining what's inside and knowing for certain whether we would be able to deflect it. Next come our briefcase-sized CubeSats. If you think of Hera like an aeroplane, then CubeSats will operate more like drones, able to take more risks, flying closer to the asteroid, carrying state-of-the-art science instruments, eventually touching down. The scale of this experiment is huge. One day these results could be crucial for saving our planet. Hera's up-close observations after DART's impact will help prove whether asteroids can be deflected, prove whether this is an effective planetary defense technique, so that if an asteroid ever poses a real threat to Earth, we'll be ready.
I'm joined by Heli Greyas, the Product Assurance and Safety Manager for ESA's Hera mission. Heli, give us a status update about Hera. Whereabouts are you at the moment?
Well, we are actually quite exciting phase because end of the last year, we had the satellite PDR preliminary design review where we see where all the equipments are put on the satellite. And now at the beginning of the year, it has been really busy days for us because we have gone through all the equipment qualification reviews. Now we are on a subsystem level, starting to see how the things are starting to come together in the preliminary phases.
It must be so interesting seeing everything start to come together like that. I'm fascinated by your job title, the Product Assurance and Safety Manager. Tell me what that role entails.
Well, I actually get this question quite a lot because it's easier to say that what engineer is doing, but what is product assurance? So my job is to make sure that all the equipments, starting from components, materials, and so on, that everything is qualified and can actually sustain the Hera environment once it's launched. Well, in Hera, since we are in such a tight schedule, we have equipment that has flown before, some who even have 20 years, first launched 20 years ago. And then you ask, but why you are looking for the components? Surely they're all qualified. But if you think, let's say television, if you think how the television looked 20 years ago and how they look now, there's a huge difference, especially on the technologies what are inside. So it's my job to make sure that all the new technologies which are inside the latest model are still qualified and can be flown.
And this qualification process, this is the way we make sure that all these components can withstand the temperatures and the radiation environments in space. It sounds like a very challenging thing to be doing. What's the most challenging thing that you're working on for Hera?
The most challenging thing is when we don't have the equipment heritage, when everything is starting from the scratch. So then you have to qualify everything. So starting, of course, you hope that there are some components which are already have been qualified. But then if there's something really new technology that we want to try, there's no previous experience, so we have to come up with a qualification plan and how to qualify in time for Hera.
It's so interesting as well. All this process that's now going on. The sort of the heritage of this idea of planetary defense and the Hera mission, it stretches back quite a long way at ESA. They were a very early space agency, I think, in recognizing the need for planetary defense. And if you go back to the sort of the 2000s, you have the Don Quixote mission study, which is sort of effectively what DART and Hera are planning to do. It must feel really rather nice to actually be building hardware now and getting this mission going after all this time.
Yes, it is. Personally, I haven't been that long in Hera project, but those one who have been there since the beginning, it was so nice to see on 2019 when we finally got the funding. And they were so happy, so exciting that we can finally start building the Hera satellite.
I cannot wait to see it launched. What would you say is your greatest sort of hope for Hera now that you're fully in there in the mission? You're invested in it. You know, you're working towards this tight schedule. It really is. What do you hope happens with the mission?
Well, there's 2 points. One is on a technical side, because it's really exciting to see a spacecraft which is kind of can do kind of a driverless car, so it goes around and without us being involved with it. So that is something that we are trying with Hera, and also of course the CubeSats that going and landing to the Dimorphos. So that's something completely new. And on the science side, of course, we are hoping to get a lot of good data that all the scientists can then go and investigate, and hopefully we will come up with a technique that how we can deflect the asteroids.
Yeah, I wish you all the best with it. And one of the most exciting aspects of this to me as well is the sort of driverless car aspect that you mentioned there. You can't really hold an orbit around these objects. The gravity isn't there, so you have to kind of constantly drive, and the spacecraft is so far away. I mean, this is really pioneering stuff, isn't it?
Yes, it is. It's really exciting. So all the team, all the industry, and all the scientists are really excited about this spacecraft.
Fantastic. Well, so are we, Heli, and we're going to keep inviting you back to keep telling us more and more about Hera as it unfolds, as we get closer to launch, and as we finally see Dimorphos when it gets to the Didymos system. So thank you so much for joining us on Asteroid Day.
Thank you.
Asteroid Day is extremely important for many reasons. One of them is we need to understand what's in our solar system that can collide with things like satellites, like space stations, and even our Earth, our home Earth. But it can also collide with other planets and kick off chunks and things and can do damage all around the universe. And so it's really important to understand all the dynamics in the solar system and in our universe that can possibly bring us harm one day. But it's also very interesting to know how things formed 4.5 billion years ago, and sending, visiting vehicles to asteroids to take samples to find out what types of life, metals, maybe we'll harvest an asteroid for its, rare materials that we can use to build a base on Mars, or maybe once we get warp drive deeper in our universe and in space, we can do some pretty cool things. And so, but you got to have that fundamental knowledge to know how to define them, where they are, and what's existing on them. And there may be life on them that can help us identify future friends or foes or people that are going to be partnering with us to explore the universe. And so it's something that we must do as explorers, is to continue to find out more about asteroids. And that's why we have Asteroid Day.
It's a shame, but living in the city, very rarely do you get to see stars.
I feel like I have a new connection to them in a way that I haven't before.
If I'm out in the desert and I look up at the sky, you just see millions and millions of places that we should be going.
It's almost baked into our DNA, the desire to go and explore, right? That's the whole reason why we left the forest and then traveled across oceans, just to see what's out there.
I was born in 1969, which is the year we landed on the moon. So I am a space baby.
When I was a kid, there were guys driving cars on the moon. They're driving cars on the moon. That's so cool, right? I want to do that.
All the rocky planets that we know of all have got a metal core in their center. And especially for the Earth, it's the source of our magnetic field. But we don't know a lot about our core. What we've learned about it, we learn indirectly, because we can't go there.
It's too hot, the pressure's too high, our instruments would melt. Can't drill a hole that deep in the Earth or other planets. It turns out we can study a planetary core out in space because there's this one object. It's one object called Psyche.
16 Psyche is an asteroid that orbits the sun out between Mars and Jupiter.
It is the only asteroid that we're aware of that is 95% metal or more and is really huge. It's about 200 kilometers across in one axis.
So it's about the size of Massachusetts.
It's believed that it may be a remnant core of an early planetesimal that was formed in the very, very earliest parts of the formation of the solar system.
And after this planet started forming and this metal core formed inside of that, it collided with other bodies that then stripped off the rocky mantle, leaving this core in place.
The first thing that came actually was the theory. Some people from Jet Propulsion Laboratory contacted me and said, we would like to plan a mission that would test your hypotheses.
And that starts you down a road that takes years. So we wrote a proposal to send a NASA spacecraft to visit this big ball of metal. And then about a year ago, Lindy gets a phone call. You win. And then we're all like, oh my God, now we have to do it.
Psyche gives us the opportunity to visit a core, the only way that humankind can ever do. And it would be the first metal object that humankind has ever visited.
We've been approved to go in August of 2022. So we talked with our mission design and navigation team, and in fact, they were able to come up with what is probably the most optimal trajectory, doing a Mars flyby.
Flies past Mars, gives us a gravity assist, uses that propulsion system to then slowly creep up toward the end of 2025, getting there in early 2026.
SSL is building the solar electric propulsion chassis. When we do the mechanical, physical integration of each instrument on the spacecraft, we'll work hand in hand with each of the providers to get out to Psyche and do a full discovery mission.
We've figured out a way for many, many people to build something together so complicated, no one person can understand it, but it all has to work together perfectly for decades without fail.
Just the fact that these things work at all is a thrill. It's just a testament to the engineers at JPL and the companies that we collaborate with, that they can build these things.
It's exciting for me to be able to be a woman winning and leading a deep space mission. The only previous woman who competed, won, and led a deep space mission was Maria Zuber, who was my friend and mentor at MIT. And so my drive is to make everyone feel welcome and to have every voice heard. We want as many undergraduates as we can. We want to involve as much of the public as we can. We want people to feel like this is their mission.
You get that first picture back, and one of the first things that goes through your mind is, oh, thank God I didn't leave the lens cap on. We will put our pictures out there as soon as they come down. So we'll discover at the same time that the public discovers. We'll be scratching our heads and it's like, I don't know what's going on. Same time everybody else is like, wow, what is that? I don't know, let's figure it out.
I did get to look at Psyche through an optical telescope in my backyard. Some wonderful colleagues brought over their telescope on a fortuitous night. It's a very, very tiny, faint dot. And that made a bunch of us cry to think that we could send something to investigate that speck of light.
We can understand this universe that we live in. We can explore it, we can learn about it, and we can be a part of something which is much bigger than just us or just this planet. We will see new things when we visit a world made of metal.
NASA's fascinating mission to view asteroid Psyche, and one can only imagine what that is going to show us. Now, one person who spent a lot of time imagining what the Psyche mission is going to show us is Lindy Elkins-Taunton. She's the principal investigator with the Psyche mission, and she joins us now. Lindy, welcome, and thank you for coming on Asteroid Day.
It's great to see you, and I so appreciate your interest in the Psyche mission. Thank you.
Now, this is fascinating to me. Asteroid Psyche, I mean, once a part of a core inside a planet. I mean, does this mean that there was once more planets in the solar system than the ones we see around us today? Tell me a little bit more about this fascinating history for this object.
The history of Psyche is such a mystery, and we're really hoping to unravel that mystery with the mission. I can tell you what theory says, what we infer from telescopic observations of other solar systems, and what we read out of the meteorites that fall to Earth today, which is that very, very rapidly after our disk of dust and gas formed around our baby sun as it was gathering mass into this baby sun, that disk of dust and gas coalesced into 1,000 or thousands of small planets that we call planetesimals, which is a great word to learn, smaller than our moon in most cases, maybe up to the size of the moon, all of them orbiting our sun, colliding with each other, sometimes breaking each other apart, sometimes coalescing together to form our rocky planets. And that's the birthing place, we think, of Psyche, of our asteroid Psyche. And our as you mentioned, our what we call our fiducial hypothesis, our number one guess, I would call it, about what we think Psyche is that it's a part of the metallic core of one of those planetesimals, one that got mashed apart, crushed apart by impacts rather than joining together to become part of the Earth or Venus. But I would just add one thing, which is that even that is an unlikely hypothesis because that doesn't happen very often in our models. And yet it's the likeliest one we've been able to think of.
It's incredible to think that it could be so rare, this object. And what kind of measurements will you be making that can tell you the truth about Psyche?
One of the most challenging parts I discover of developing a mission is figuring out what we can measure. It's all so much harder in space than it is on the Earth. And there aren't that many instruments to choose from, and what measurements can they make and what can we infer from them? Well, so we start by what can we infer from the Earth? So we think we know about what the density of Psyche is, which says that it can't be pure rock, it has to be denser than that. And the only thing really common that's denser is metal. It has certain aspects of how light reflects off it and how radar reflects off it that says that it should be metal. And so what do we do with that when we get there? Well, the number one thing, which I think almost anyone could guess, would be we carry a magnetometer to see if it has a magnetic field. And we hope that it does, because if it has a strong magnetic field that it's still holding on to 4.5 billion years after its formation, then that does mean it was once a core. We'll take pictures, of course, because never go to space without taking pictures. General rule of thumb, always bring cameras. And then the last instrument we're bringing is called a gamma ray and neutron spectrometer. And that is a really astonishing high-tech instrument that will be able to measure from orbit, we're just orbiting, measure from orbit the atomic composition of the surface of Psyche. And we are very, very excited about that. And so along with that, we'll measure its gravity field and its shape. And of course, we'll get its density. Those are the things we'll be observing when we're there.
So the Psyche mission itself is about a year away from launch. How does that feel to be entering this sort of final stretch?
It is so intense in this final stretch. Everyone warned me. I've never been on a mission in this stage before. And so I'm experiencing it for the first time along with a few of our team members. And we just look at each other and our eyebrows go up and our eyes get big. So indeed, we're in this phase called Assembly, Test, and Launch Operations, which of course is known as its acronym ATLO. And we are less than a year from launching the spacecraft, or from transporting the spacecraft from Jet Propulsion Laboratory in California to the Cape in Florida for launch. So in less than a year, it'll be going across the country to Florida. And then in just over a year, it'll be launching. And so one might think in the normal projects that one does in one's life that a year is plenty of time to do most anything. Well, keep in mind, we've been working on this project, the first concept 10 years ago. And then we were approved by NASA for flight in 2017. And so we've been completing the design and then building ever since then. And now it feels like we're down to the wire. We have literally every day planned what needs to happen with every part of the team to make this happen, to get to launch. And you can also imagine that it is much more challenging to do this when the Earth has been going through this pandemic, because you cannot literally build hardware remotely. You cannot build hardware over Zoom. And so making sure everyone stays safe, opening the labs to the capacity that's possible, keeping all the parts rolling in, it's been a big challenge, but we're feeling confident that we're going to make it. But it's stressful. It's a high stress year.
Well, I've got every confidence in you and the team, Lindy. I really have. And if I ask you, what would be the one thing that you would like to sort of see at Psyche or to know about Psyche by the mission, what would be the one thing that you would choose?
Oh, what is the one thing that I most want to know or see? Well, I'd tell you that of course, I hold all of our science objectives dear, and I will be my correct, impartial scientist self as we read the data and come through. But what I want to share with you right now is my real gut reaction is two different fantasies about Psyche. One is I can't wait to see what it looks like. I'm really hopeful that it looks quite different than other asteroids that we've seen, because we're pretty confident that it's a large percentage metal. It could still even be all metal, and maybe half metal is also a possibility. So it could look very different, and I'm hopeful that it will. I think that would be exciting. And here's the other thing I hope. I hope that all our ideas about what it is and how it formed are wrong, and that we get a big surprise, and that it's something we never anticipated. That would be a great payoff, actually. We'd learn even more from that.
Well, we are all on the edge of our seat to know what Psyche really is, and we'll be with you every step of that way. So thank you so much for joining us on this Asteroid Day. We're really very grateful.
I'm very grateful for your interest, and we're so excited to share everything about this mission with everyone. Thanks so much.
Observing and visiting the asteroids of the solar system has provided a whole host of challenges and opportunities for astronomers and engineers and scientists. I'm joined by Andy Chang, who's the lead investigator of NASA's DART planetary defense mission and a former project scientist for the Near-Shoemaker mission, our first dedicated mission to an asteroid 25 years ago. Now, Andy, you've seen the evolution of space technology, such as propulsion, communications, and others at first hand whilst working on these missions. And what is it, do you think, that makes tracking, characterizing, deflecting asteroids, possible these days? What are these key technologies for you?
Well, the key technology for DART that allows it to hit the asteroid actually comes from the missile defense world. It's the ability to zoom in, home in on a target autonomously that you see in your camera and be able to hit it. So that's where that comes. Of course, the ongoing advances in electronics. So these guys, miniaturization of electronics, things that computers, sensors, everything much smaller now than they could be with NEO. For example, the spacecraft electronics were several boxes the size of, as I'm trying to show, several boxes that size. On DART, all those functions are in a single box. So because the electronics have been miniaturized, capabilities have just increased, all around.
Yes. And is that the key technology, you would say, is the miniaturization of the electronics, or are there others that are equally important?
It's that, and no, I think that actually is that everything can be done more integrated and smaller, cheaper, and also faster now than 25 years ago. We could not have done the DART mission. It would have been a much more expensive, a very large, much more expensive mission.
It's interesting you raise the point about cost effectiveness in missions, because there are now 5 fully funded asteroid missions set to launch in the next 3 years. Each of these missions has a different set of scientific objectives. I'm wondering what the common themes in our asteroid research is these days.
Common themes, we always want to discover what kinds of materials these asteroids are made of. For different purposes, some of them want to explore the early solar system, how planets formed and how these asteroids formed, and we're looking for the primitive materials. In some cases also, the objective is to characterize what resources they may be found on asteroids. And another common theme is the study of how the asteroids are put together. What is their internal structure? Are they rubble piles, just loose piles of rock and powder, we call regolith, so it's powdery material that are just held together by their own gravity mostly and minimal strength, or are they actually more strongly glued together, if you like, because they're actual rocks? So that's also a big question. We want to know for a number of reasons. One of them is that for planetary defense, it makes a big difference if you're about to be hit by a fluff ball or very loose agglomeration versus a solid rock or even a chunk of metal. So that makes a big difference. It also makes a difference to you if you want to mine something, whether you're going after a rock or a powder material. So these are that's a common theme also to try to understand in asteroid exploration.
It's very interesting, isn't it, how all of these ideas about what is an asteroid, what's its composition, what's its internal structure, it feeds into all the other questions that we may have about asteroids. What role did they play in the origin of the solar system? How could we deflect one? Does it contain resources that we might one day want to mine? Now, I've had immense pleasure in talking to you today, Andy. I really have. It's been so fascinating to hear your stories about NEO and your look into the future with DART as well. You truly are an architect of our understanding of asteroids. You really are. I want to ask you one question though before we go, and that's I want you to dig deep and tell me what is the one thing that you would love to know about asteroids that we don't already know. And on top of that, if there was one technology that I could magically make happen for you that would allow you to do something with asteroids in outer space, what would that be?
Well, the one thing actually that I'm losing the most sleep over, because I want to know, is how strong these asteroids are. We think they are, they must be glued together at some level, but maybe really, really weakly. And we've never been able to measure very well how hard it is to pull an asteroid apart. So that's what I'd like to know the most, yes.
So perhaps if I could give you a magical technology then, it would be an asteroid-sized centrifuge or something like that, that you could spin an asteroid and see how much it takes to pull it apart.
Yes.
If you can't have that, however, how will we answer your question?
Well, it's actually much more complicated because no doubt it depends on what exactly you're trying to do. If you want to dig in it, that'd be one thing, because you want to, make a hole, you want to extract materials for resources. If you want to push it aside, you want to do that in a way that you don't break it up into other small pieces. Okay, that's maybe a different answer if you do it that way, because it depends on how fast you're trying to push it and also what the scale size is. It's a very complicated question. There's not going to be a simple answer. So I don't even know if one toy could do it for me. It would be many, many toys.
And it's going to keep you very busy for a long time. So,
Yes.
Andy, thank you so much for sharing all your insights and your stories with us today. We're so grateful that you joined us.
The Lucy mission is going to fly past 7 asteroids in 12 years with 1 spacecraft.
We are going to an amazing variety of objects with this mission. And it's really almost pure luck that allowed us to get as many rich targets as we are. Literally, the planets were aligning to allow us to do this mission.
The Lucy mission is named after the Lucy fossil, the Australopithecus fossil that was discovered in the 1970s in Ethiopia. And just like the Lucy fossil transformed our understanding of hominid evolution, the Lucy mission will transform our understanding of solar system evolution.
Trojan asteroids are an interesting population of small bodies that are left over from the formation of the planets, and they lead or follow Jupiter in its orbit by roughly 60 degrees. If you just look at the gravitational attraction of the Sun and Jupiter and put something exactly 60 degrees in front of Jupiter, it's stable forever. So as a result, these objects are really the leftovers of planet formation. The stuff that went into growing Jupiter and Saturn are now trapped in these locations.
The very first asteroid we get to is a main belt asteroid named Donald Johanson. We named that asteroid in honor of the researcher who found the Lucy fossil. We're going to use that asteroid to do a rehearsal on our spacecraft to make sure everything is working properly so that when we get to the Trojan asteroids, we're ready to go.
We're visiting both of the Trojan swarms. In the first orbit, we're going into the leading swarm, and we're going to encounter 4 Trojan targets.
Eurybates, Ptolemy, Lucas, and Oris. And from this, we're going to sample the diversity in sizes and colors and compositions. The first 2 flybys happen just about 30 days apart, so it's going to be a pretty busy kickoff to the season of exploring the asteroids in the L4 swarm. And then we'll fly past Earth again and out to the L5 swarm.
The final object we're visiting, which I must admit is my favorite, is a binary object.
So that's 2 Trojans that orbit a common center of mass. It's called Patroclus and Menecius.
These objects are nearly identical in size that orbit one another.
From the Lucy mission, we're going to study the diversity of our targets because that tells us something about their origin and where they came from.
The interesting thing about small bodies in general is they are the leftovers of planet formation. If you look at the 8 planets that we know about, for example, they are highly processed because of internal processing. These asteroids are objects that really haven't changed much from when the planets assembled themselves. And as a result, by studying them, we can figure out the physical conditions of the early solar system, as well as how the planets grew and how they moved around early on.
All of that will help us form a detailed picture of what these objects really look like. Because right now, our best images are just a point of light. Even using the Hubble Space Telescope or adaptive optics on large ground-based telescopes, we can't see surface details. And it's going to take the Lucy mission to go to these targets and see what they're really made of and what they look like.
NASA's Lucy mission there, an ambitious endeavor to take us to some fascinating destinations. Here to tell me more about this extraordinary mission and its equally extraordinary targets, I'm joined by Lucy's Deputy Principal Investigator, Kathy Olkin of the Southwest Research Institute. Kathy, welcome and thank you so much for joining us today.
Hi, Stuart. Thanks for having me.
It's a pleasure. Now, the Trojan asteroids, I mean, goodness, even the name sounds exotic, and I am betting there's some pretty big secrets out there to be revealed.
I think that's exactly it. They're mysterious. We've never sent a spacecraft to the Trojan asteroids before, and I can't wait to see what we're going to see when we get there. Anytime we've looked at a new population of objects, it's really advanced our understanding of our solar system. And these Trojan asteroids, I expect, will be the exact same thing.
Now, Lucy's all tooled up as well to sort of really get the details. Tell me a bit about the instruments and the measurements you're going to be taking so that you can build up this picture of this new family of asteroids.
Yeah, I like to think of our instruments as the eyes that we're going to have on the Trojan asteroids. So we have 3 scientific instruments. LORRI, which is kind of a small telescope that'll give us black and white images, high resolution images, so we can learn about the geology of the Trojan asteroids. We have the RALPH instrument, which is really 2 instruments in one. It's going to give us color information, so visible color, and then infrared spectra so that we can understand the composition of the surface. And then the TESS instrument will help us determine the temperature of the surface, and also a property of the surface called thermal inertia, how well the surface retains the heat. And also something we're doing interestingly is that we have the 2 of the subsystems on the spacecraft are going to contribute to our scientific return. We have terminal tracking cameras that will help us keep our scientific instruments pointed at the target. And these terminal tracking cameras will also help us to understand the volume of these Trojan asteroids. And our telecommunication subsystem is going to help us understand the mass of these Trojan asteroids. As the spacecraft flies by, the gravitational pull of the Trojan asteroids will change the velocity just a little bit of the spacecraft. And we'll be able to measure that with the Doppler signal through our radio subsystem. And that's going to be so exciting. And we can combine the mass and the volume to understand the bulk density of these objects. So there's a lot of investigations we're going to do across a large part of the electromagnetic spectrum and really getting a broad look at the surface properties and interior structure of the Trojan asteroids.
One of the things that I love so much is how creative scientists and engineers are when they make these missions. So, you're describing using these subsystems which are there for telecommunications and navigation, but you can extract science out of that as well. It's just squeezing every little bit of information out of every bit that you get back. I just wonder, out of all the breadth of everything you're going to be looking at, if you could know one thing about the Trojan asteroids at the end of the mission, what would that be?
Probably the thing I'm most excited about learning about these Trojan asteroids is the composition. What are they made out of? And so there's the surface composition, which we'll get from the infrared spectra, and we'll be able to look at minerals and organics and ices. And then also the bulk density gives us information about the composition. So I probably picked 2 things rather than the one you were asking, but those are the things I'm most excited about learning about the Trojan asteroids. And the reason I really want to understand those parameters is because that helps us understand where these objects came from, what their history was. These are really the leftover building blocks of our planets. And so really understanding this small body population is going to help us understand the evolution of the solar system.
Well, after all the work and the dedication that you've put into this mission, I think we can allow you two things rather than just the one.
Thank
Now,
you.
you're looking very calm at the moment, which is quite interesting because you're racing towards the launch at the end of the year. And I imagine there is 1,001 things to do. Bring us up to date with what the current status of Lucy is.
There are so many things going on right now. You are exactly right. And it's a very exciting time. For a long time, the mission concept was just that, a concept. It was on paper and it was an engineering design, computer-aided models, things like that. Then we got to be actual physical hardware. And right now, all of that hardware is assembled as the spacecraft. And we've been through a lot of our environmental testing program. So we've done vibration tests, electromagnetic tests. And right now, right today, we are in what's called thermal vacuum testing. And this is going to go on for about a month. And we are going to be testing the spacecraft in a vacuum chamber. So you evacuate all the air so that we can simulate being in space, and we can change the temperature, because Lucy is going to go launch from near Earth, and then go out to near Jupiter. And so that's quite a range of heliocentric distances, quite a range of temperatures, and we're going to test across that temperature span to make sure that the spacecraft and all the systems are going to work well together in the conditions that we need. There's a saying called test as you fly and fly as you test. And it's pretty exciting because that's what we're in the middle of right now. We're testing as we plan to fly.
And it's worth pointing out as well to any viewers that haven't seen the spacecraft, Lucy has the most beautiful solar panels that have ever been flown into space. It's a lovely looking spacecraft.
Yeah, they are magnificent. They're absolutely beautiful. And to think that they'll provide the power that the spacecraft needs so that we can get those eyes on the Trojan asteroids and get that data back to Earth. It's all quite remarkable and very exciting.
Indeed it is. And I can assure you that we'll have eyes on you, having eyes on the asteroids in the Trojan points round Jupiter. So Kathy, thank you so much for joining us today and bringing us up to date with the mission. We look forward to more updates in the future.
It was nice talking with you. Thank you.
Welcome to my laboratory. This is a place that I have full of telescopes that I ship all around the world for the purpose of measuring the shapes and sizes of asteroids. Asteroids that could be close to the Earth that might actually hit us, or they could be objects that are well out beyond Pluto. With these relatively small telescopes here, we can do all of those things with the aid of lots of amateurs and teachers and students to help me make these observations. I get asked a lot, what is an occultation? And this is when something moves in front of something else. In this case, it's an asteroid moving in front of a star. And what you see on the ground with a telescope is you see the star, you don't see the asteroid. And if you're in the right place, as the object moves, it passes in front of the star and you see the star disappear. It depends on the size of the object, but it can be a very short period of time, like half a second or less, or it could be very long. And by that, I mean, it could go away for 10 seconds. It's still pretty short on the grand scheme of things. So if you know the position of where you're standing on the Earth, and you know when you are observing, when the star disappears, that's a point that you can relate to the object. And then when the star reappears, that's another point. And if you have different observatories in different places on the Earth, they all get different hits on the side of the object. You put it all together and you can actually create a connect the dots picture that will show you the outline of the object. This year has been a very busy year already, and it's going to get busier as we go on through it. One of the first events that we chased was the famous asteroid Apophis that made a close pass to the Earth. And we put out 60, 70 different people and telescopes to capture this tiny chunk of rock. But the work that I'm doing for the rest of the year is studying the targets for the upcoming NASA mission called Lucy. Lucy's going to launch in October of this year, and we're going to fly out to 5 different targets, which has 7 different bodies to study and look at. And I'm the advanced crew. I'm the one that's going to kind of do the advanced scouting of the targets, try to learn as much as possible here from the Earth about them so we can better plan the observations with the Lucy spacecraft. And this fall, in October, we're going to be sending these big telescopes behind me. We'll all go to Spain to study the object Polymele. This is the smallest of the Lucy targets, and there are some critical issues that we have to work out for the mission. It's kind of the highest priority target. Then just 16 days later, the small versions of these telescopes will be in Senegal, and I'm sending them there to be used by local observers to measure the object for us. You might think, why go through all this trouble? We're sending a spacecraft out there. You would think that spacecraft can do everything. We can just send it there, you'll learn everything you want to know about it. There's some things that you have to know ahead of time that it's important for the planning. So for instance, how bright is the surface? We need to know that. If it's super, super dark, then you need to take long exposures to make sure to get enough light off the target. If it's super bright, you need to take short exposures. So that's kind of the first basic thing. And we know that all of these objects are really dark. We've kind of gotten that past that part. There's another aspect is that one of the goals of the mission is to figure out what the density of these objects are. By using these occultations and getting a limb outline of the body at different times as it rotates, we can actually improve the measurement of the density for the spacecraft. So this is actually more than just advanced planning, but it is also complementing and enhancing the science that will ultimately come out of the mission. Out of all the work that I've ever done in astronomical observations and studying the heavens, this particular type of project is the one that is perhaps the most accessible to the general public. All you got to do is have a telescope and a camera and the willingness to be up at night every once in a while. But the technology is so much better now that it is actually pretty easy to get involved. There's a worldwide organization of amateur astronomers that participate in the Occultation Timing Association, sanctioned by the International Astronomical Union. And they all work together to common cause to chase asteroid occultations. They help me out occasionally from time to time. Also, I have another project, Recon project, that involves teachers and students in the Western United States. We've got more than 50 schools involved in this, and we're teaching the next generation of astronomers through this project. It's one of the best so-called citizen science projects that I've ever run across. And then finally, I actually reach out and recruit people all around the world. Anytime I go and take this traveling circus of all these telescopes, like when we're going to Spain, I reach out to the locals in the area and try to get people involved. That's how I've engaged the people of Senegal to help out. And they managed to get us through some rough patches here with the pandemic, where I couldn't travel there to help with the observations, but I can still send them equipment. So all you got to do is be able to have a decent sized telescope, and it doesn't have to be as big as the ones behind me. There's still plenty to do. And there's lots of ways to get involved, but it's a very rewarding experience. And I will tell you this, out of all of the amateur astronomers that I've ever met that have never done an occultation, they all kind of get tired after a while. You know, how many times can you take a picture of some nebula or galaxy or set of stars before it's, well, they don't change, they don't do much. So I talk them into trying out an occultation. And everybody that tries one of these things and does it on their own is hooked for life. They're an immediate convert to doing science with occultation.
So I have an asteroid named after me. It's called the Melvin, which is really, really weird. I was a little kid from Lynchburg, Virginia, a small town. Never imagined, going to space or being an astronaut or anything. And now to have an asteroid named after me is very, very humbling. So asteroid Melvin 108096 was named that. It's the order in which the orbit of the asteroid was basically well-defined, because asteroids can have these wildly elliptical orbits and be going all over the place. And so until you mathematically define its actual orbit and where it's going and coming back to, that's when mine was discovered and named. So it's pretty wild. I'm 108096 Melvin. Crazy.
はじめまして。JAXA 宇宙航空研究開発機構火星衛星探査機 NEO-MAPP プロジェクトの戸梶です。この度はアステロイドデイライブにおいて JAXA が開発を進めている火星衛星探査計画 NEO-MAPP についてご紹介させていただく機会をいただきありがとうございます。火星衛星探査計画 NEO-MAPP は2024年度打ち上げ、2029年度地球帰還を予定している火星衛星フォボスからのサンプルリターンミッションです。このミッションは、はやぶさ2に続く JAXA の小天体探査戦略の中核を担うミッションです。重量は約4トンと、JAXA の新宇宙探査機では最大級の大きさになることが想定されております。現在開発中の日本の次期基幹ロケットである H3 ロケットで、種子島宇宙センターからの打ち上げを予定しております。NEO-MAPP のミッションは、火星の衛星フォボスのサンプルを採取することによって、火星衛星フォボス、ダイモスがどのようにして誕生したのかを明らかにするとともに、太陽系の中で水や有機物がどのようにして惑星に供給され、生命が誕生、居住可能な環境ができたのかを明らかにします。火星には2つの衛星があります。火星に近く大きな衛星がフォボス、遠くにあって小さい衛星がダイモスです。この2つの衛星には2つの点で小惑星に似ていると言われています。1つ目はその形です。はやぶさ2で探査を行ったリュウグウなどもそうですが、小惑星は惑星のような球形をしているわけではなく、ゴツゴツとした不規則な形をしていることが一般的です。フォボスとダイモスの形も球形ではなく、ジャガイモのようないびつな形をしています。もう一点は表面で反射する光の波長、反射スペクトルです。反射スペクトルは小惑星の表面物質に影響されますが、フォボスやダイモスの反射スペクトルは D 型小惑星に分類される小惑星の反射スペクトルによく似ています。D 型小惑星というのは色がとても暗いのが特徴であり、波長が長い赤色や赤外線がわずかに反射される程度です。火星衛星探査計画 NEO-MAPP にはフランス、ドイツの宇宙機関が開発を担当するローバーが搭載される予定です。今回 NEO-MAPP に搭載されるローバーには車輪があります。その車輪を使って火星の衛星フォボスに着陸後、動き回ることができます。車輪は地面との摩擦力によって滑らずに動くことができるのですが、地球の2000分の1しか重力のない火星の衛星フォボスの上では摩擦力がとても小さくなります。つまり、車輪がとても滑りやすいということになります。そのため、車輪の形を工夫するとともに、シミュレーションを行うことで、 そのような移動しにくい環境でも安全に移動できるような設計を行っています。火星衛星探査計画 NEO-MAPP では、はやぶさ2などの他の小惑星サンプルリターンミッションとは異なり、火星の衛星フォボスに着陸脚を使って着陸します。着陸技術を確立することによって、タッチ&ゴー方式では実現できなかった小天体上での長時間の活動が可能となります。その結果、地表を観測し、障害物を避けながら最適な場所からサンプリングをするなどの複雑なミッションが可能となり、将来の小惑星探査の選択肢を大きく広げることができると考えております。火星衛星探査計画 NEO-MAPP は2024年度の打ち上げに向けて鋭意開発が進められております。その様子は公式 Twitter アカウントからのツイートやブログ記事など SNS を通じて日英両語で発信しております。ぜひご覧になっていただければ幸いです。ありがとうございました。
However we look at it, asteroids are going to play a big role in our future exploration of space. They're cosmic time capsules from the birth of the solar system, and they contain resources that can be used in our exploration of the wider solar system. But to get at those resources will require technology and techniques that currently sound a lot like science fiction. I'm Mary Lynn Dittmar, Executive Vice President for Government Affairs, Axiom Space, and formerly CEO for the Coalition for Deep Space Exploration. And in this panel, we're going to talk about the future of exploration, utilization, and commercialization of space, and what that means in reality. And to do that, I'm joined by Matthias Link, Director, Space Resources.lu and International Affairs for the Luxembourg Space Agency, and Interim Director of the European Space Resources Innovation Center, Franco Ongaro, Director of Technology, Engineering and Quality for ESA, Roy Pinto, Chief Technology Officer for SES, and Anusha Ansari, Private Space Explorer and CEO of the X Prize Foundation. Matthias, I'm going to start with you. When people hear the term space resources, they may think of precious metals that cost a lot on Earth, but it's more subtle than that. So what do we really mean when we say space resources?
Thank you, Marilyn. Yeah, it's indeed much more subtle than looking for the typical golden asteroid that is often mentioned in connection with space mining. Space resources do not only include precious metals, but metals in general, and also various gases and water. And in the short term, it is about using them in space rather than bringing them back to Earth. So we can imagine today that these resources will be used for various applications in space, both supporting, as you said, the further exploration of our solar system, but also laying the basis for the future space economy. And to give you some examples, for example, water and oxygen can be used as life support for astronauts. Oxygen and hydrogen can be used as propellant for rockets and for spacecrafts, for example, allowing in-orbit refueling and more generally in-orbit servicing of satellites. And metals and regolith from the moon, but also from asteroids, can be used for building various infrastructures or housing, but also for manufacturing equipment like solar panels or larger antenna. So in general, we believe and we are certain that all of this will allow us to be less dependent on expensive launches from Earth, allowing a more sustainable and more efficient space economy and more generally space activities to the benefit of everyone.
So that is a lot. It's a mouthful that you just said. What are the main goals for the European Space Innovation Research Center?
Yeah, the European Space Resource Innovation Center, in short, ESRIC, it's a joint initiative between the Luxembourg Space Agency, the European Space Agency, and the Luxembourg Institute of Science and Technology. And it's a new innovation center that we launched in Luxembourg in last year, in 2020. And it's for us a further step within the Space Resource.lu initiative that we launched in 2016, 5 years ago. And overall, with ESRIC, we aim to establish an internationally recognized center of expertise, specifically for scientific, technical, but also business and economic aspects related to the use of space resources, both for human and robotic exploration, but also for a future in-space economy. And we will cover different aspects in ESRIC, and I do not have time to detail them, but we'll try to establish research and labs all along the value chain of research of space resources. We will launch a dedicated startup support program to support startups in this domain and also enable commercial partnerships. We also work in bringing together the European and worldwide community around this topic in Luxembourg, for example, with events like the Space Resource Week that we recently organized with more than 1,000 participants. And we'll also work on different tools to establish a knowledge management base to get track this rapidly evolving field of space resource utilization.
So with a program that's as broad as that program is, it sounds tremendous. How much of a focus do you actually have on asteroids specifically?
Yeah, very specifically with ESRIC, we really want to focus on all different locations where resources can be used and can be brought to applications. So both the moon and asteroids, but later certainly also Mars. And actually we have already today an experiment on Mars that is using the Martian atmosphere to produce oxygen on a NASA mission. But it is also undeniable that there's a strong focus right now on the moon and its resources, with a lot of different missions that are planned, both private and public. However, in the medium term, we are quite sure that the focus will also shift again more to asteroids, because of course they have also some advantages like low gravity, some of them very near the Earth. And so for some resources, it might be actually much easier to access them on asteroids. And overall, and of course, that's also why we talk about space resource utilization in the context of Asteroid Day, there are a lot of synergies between space resource utilization and planetary defense in terms of getting a better understanding of the location and the different properties of asteroids.
Thank you. We're looking forward to seeing your work as it continues to evolve over decades. It sounds like you certainly have a extensive program. Franco, turning to you, can you tell us about ESA's space safety program?
Yeah, when working on new missions, we looked at missions to detect and alert from solar flares, so that would be space weather missions. As you point out, the environment around the Earth is part of our environment, so clean space and keeping our orbits clean and sustainable for the future. And as part of this program, another mission was a long-studied one, but finally restarted thanks to NASA, the one that will protect us from strikes of asteroids, and that is the HERA mission. So these three missions, ADRIOS for capturing and re-entering a piece of debris, L5 for space weather, and HERA are constituting the first three missions of the space safety program, which is really looking at safety from threats from space.
So asteroids are part of that larger space environment, right? And when we talk about space safety, sometimes it doesn't really occur to people that we need to be thinking about space as an entire environment and very dynamic environment. Extending the concept of space as an environment to national objects, you were responsible for the study of ESA's asteroid deflection mission Don Quixote in the early 2000s. I remember this. That was the beginning of the path that led to DART and then also to HERA. How does it feel to be on the cusp of these missions launching?
Well, it feels great. It feels great because it's been, I would say, most of all, a human adventure. It took a few dreamers back in 2000, Andrea Milani as a scientist, Anders Galvez, my colleague in ESA, to come up with a Don Quixote idea, among other ideas. We had a science team. And then we didn't manage to get it funded by our member states, so it seemed like the idea was abandoned. And that the National Science Foundation in the US picked up the idea and told NASA, you should do a mission like this. And NASA was kind enough to come back to us and say, do you want to cooperate? And there we managed, not without some difficulties, to finally get Hera underway. And in November, that will be launched, and Hera will be doing its CDR next year. So we're already planning working 3 shifts to be able to launch in 24. And I'm sure we do our best to keep that date. So it's both excitement and worry, but that's the life of a manager. So that's okay.
It's true. Your key role in ESA is to develop the technologies that we need in the future. How do you go about identifying those technologies?
Well, first of all, I rely on a lot of smart colleagues, which are much smarter than me. But overall, I think we'll go along 2 paths generally. The first one is the most exciting one. We have scientists, we have communities, like, for instance, telecom, coming to us and saying, well, we want to push a lot more bits for a lot less euros. How do we do that? And that means trying to improve on what you have. And there it's really working. And sometimes you have to abandon the way you do things and move to brand new technologies like light, which gives you a lot more bandwidth than RF does, with constraints in terms of pointing, etc. The other part is our darling scientists who come up and want to measure things that have never been measured before, like spotting, like keeping Gaia pointing like enough to spot a 10-cent piece on the moon from the Earth. I mean, I admit there must be easier way to find money for science, but that gives you an idea of the type of challenges that then get us to work on really new technologies.
More bets for more euros, also part of the life of a manager, yes? One essential part of our future in space, is, speaking of technologies, is communications. We're going to need to talk to all of these spacecraft and astronauts that are out there. So Roy, moving to you. SES is a part of the ESA Moonlight Initiative, which, for those who aren't following it, also involves placing a consortium of satellites around the moon. From a technology point of view, how difficult is it to maintain contact with deep space missions?
Thanks, Mary. That's a good question. In fact, it could be a question for Franco, right? Because ESA and NASA have pioneered communications to deep space missions. And the difficulty starts with the fact, first, there are the more obvious challenges, right? Deep space missions are far away. You have minutes or hours of delay. The signals are very weak. So you have those facilities, those huge antennas in Chile, Australia, Spain, and other places that you see in science fiction movies that track deep space missions and provide vital communications to them. The idea behind, we're very proud to be part of the Moonlight project. The idea behind it, and we're working with Space Survey Technology and other partners, is to make it easier. And to make it easier, you have to try to deploy as much commercial space technology as possible. Right now, as I started explaining, if you want to talk to a probe that is going through Jupiter or so, you need huge antennas, a lot of customized technology. If we can deploy smaller satellites around the moon, or if we can have interoperable inter-satellite links, then it makes it much easier to provide that communication. And as the number of probes and missions grows, you have the scale to help with that. Right now, most private constellations don't have inter-satellite links. And if they do, they're just inside a constellation. There isn't a standard for satellite A to communicate to satellite B and hop from one place to another, like you have, when you are roaming with your phone. So for me, making it commercial, simpler, and using technology that we are using on Earth are the steps that are required to make deep space communications simpler and cheaper.
I think a lot of people don't recognize how important communications is in mission planning and how much it actually drives mission planning. When I was helping to develop the International Space Station, you know, we needed to pay a lot of attention to when station would be available to comms networks that were already in existence. What lessons from Earth's satellite communication networks can we apply to deep space exploration, do you think?
There are a number, and it wouldn't be fair to say that they all come from space, right? We shouldn't be afraid of telling that we borrow the technology that is used in other areas. So, for example, at SES, we are creating a multi-orbit architecture that is interoperable. The satellites can talk to one another, and if you are a customer on Earth, it shouldn't matter if you're using a low Earth orbit, medium Earth orbit, geo Earth orbit, moon, whatever satellite you're using, it should be transparent. And the way to make that transparent is to have a software layer that will standardize and make the assets that you're using transparent to the asset that needs that communication. What SES and other companies are doing is investing in software automation, AI, and developing standards that allow us to hop from orbit to orbit or from constellation to constellation seamlessly for the customer, the user, or the mission. That's where we have been investing. There's a lot of innovation around that because there aren't any standards. So sometimes we can borrow standards. We look at 5G, part of the satellite industry is looking at 5G and seeing how it can make itself interoperable, and part of the 5G and 6G architecture. We have developed software that makes our MEO satellites, medium Earth orbit, geo satellites, geostationary orbits, transparent to our system and to the users. That's for me the key. The key is on making it software programmable.
And given that key, there's a lot of satellites that are being planned and launched now around Earth. How do you see that impacting connectivity on Earth space and also communications with other possible exploration targets?
There is a good and a bad side to that, as many of us in the industry know. Space is a scarce resource. It's one of the common goods that the United Nations has defined. If we are not careful, certain orbits will become congested. And if we have a collision or collisions, they may become unusable. We have a mathematical model that will predict that. So we have to develop guidelines, standards that are enforceable, that keep that ecosystem, that preserve that ecosystems for us to use. So the bad side is that there isn't a lot of regulation. There are some guidelines, but they are not internationally accepted. The good side is that there is a ton of technology coming. I was mentioning software-defined satellites, we call them STFs, and you look at new constellations in any orbit, most constellations are trying to make their satellites programmable so that you can update them without having to launch another one. So a mix of technology coming, making satellites programmable and more flexible and maneuverable, and international standards that are agreed and enforceable between agencies and administrations, those two coming together will make sure that we can use for quite a long time and we can still see the stars, we can communicate, and we have better and pervasive space-enabled communications on Earth.
And all this goes back to, Franco, what you were talking about with regard to thinking about space as an environment, really. And then also, Matthias, we're going to need a lot of that innovation that you're working on. There was a time, though, when space exploration was the sole province of national space agencies of large countries such as the US or Russia. Now, however, advanced technology and techniques are allowing smaller countries and private companies to reach beyond the Earth. This creates a competitive environment for businesses to innovate. The X Prize fosters this sense of competition as a way of driving innovation. Anusha, how does the X Prize view space and its value to Earth?
Mary, if you know our origin story, our start comes from space. And when my family and I sponsored the first competition that was actually pushing the boundaries of commercialization of space, hoping that it will bring a new generation of space explorers and also space innovators. And it proved to be very successful. And at the center of that, it was a belief that we will do better if there is more collaboration between the public sector and the private sector, and working with the space agencies to bring them together and see the private resources as a way to be more efficient, to have more ideas, and sort of expand the lens of how we can explore space and become spacefaring species altogether. We have since then launched other space exploration competitions. The Google Lunar X Prize, we call it our most successful failure because the prize was not won, but it really spurred so much excitement around the globe, where teams were formed in countries that didn't have a space program, and those teams sort of became the center of a space program that is now flourishing. Many of the teams who did not win, their technologies that are now developed further are being used by the space agency. So it's very exciting to see how the competition can really broaden the horizon of where space innovation can come from. So we continue to push the boundaries and looking at ways that we can use the tool of the competition to find more solutions that opens up more of the space to everyone here on Earth. But we also, as you mentioned, we don't look at the space just a place to go. It's a field of, imagination, where you can really expand your imagination. It's a source of innovation and knowledge for us. When we are anywhere we want to go, we look at a map, and the first thing we want to do is find ourselves on the map. And we have an immense map of this universe that we're still charting, and we want to find our place in it. And I think exploring it, learning about it, using its resources to better our world, to better understand our own world and our place in it, and how we can preserve it. It's all areas that X Prize and our work in space will try to push further.
Thank you for that. Did your time in space change your vision of the future and how technology in space can be a part of that future?
It did, because I had this amazing experience of flying with someone who was my station commander, who's now part of Axiom Space. So you know him, Mike LA. And he didn't see any value in commercial space programs. And, so before my flight, we had these conversations, debates around it. And through the time we spent together on space station, and by the time I returned, I managed to open a window in his mind. So to me, there were many people where bringing commercial space partners into the program was something that they didn't think it's a good idea. And a lot of them have changed. And we've seen now the rate of innovation has accelerated significantly because of those partnerships. Are they perfect? No, nothing is perfect. But it's a great start. And when I was on the space station and looking at technologies around me and coming from a technology background, being a tech entrepreneur, I could see the difference between what's available and accessible to the astronauts and the space program is so far apart from what others are using, the innovations that are in the other industries. So I saw a great opportunity of giant leaps if we collaborate more. And it was necessary because you open your lens when you're on space station, you can see our planet as a whole, and you understand our interconnected ecosystem, and you really feel the fragility of our environment. So it becomes apparent and essential to create more collaborative programs around the globe, and for the different space agencies and countries and government to work better together, because there's so much to be done, so little time. Asteroid Day is a good example of how things can strike, and unless we have global preparedness for it, we won't be able to protect ourselves. So these types of large-scale programs require collaboration. So that becomes apparent when you're on a space station that is there because of collaboration of many countries.
So I couldn't agree with you more. Space station has been part of the thread that's run through my career. I often say I started by helping to build one, and I'm probably going to end it helping to build another, its successor. And so LA does speak frequently of the experience of flying with you also, and how it opened his mind to these collaborations. So it's had a lot of impact on sort of next generation work. What's the thing that excites you the most about the future?
I'm excited because I see a new era of exploration, and not just going someplace and coming back, but going and, staying. I'm excited about seeing a base station on the moon, and maybe hopefully one day even visit it. But I think for us to be able to go further, we need to be able to spend extended amount of time in space and learn how to live in space. Living on space station is one thing, but living, in a permanent base station where it's manned, and we need to create a way for us to sustain living there. I can't imagine a better place, a better training ground than the moon. We talk about Mars, we talk about other moons. So I think I'm excited to see that going further. Hopefully, like many programs, the budget cuts doesn't put it in a tailspin again. But this time there are, again, a lot of commercial companies involved in it. And I think even if the space agency budgets gets cut and it causes delay, I think the private sector is really excited, and they will push those boundaries and carry it forward. There's this new word about the lunar economy now. So when I hear lunar economy, I'm like, okay, we've arrived. We've changed mindsets that people can look at the moon and see a lunar economy. And the moon is part of our ecosystem. When we talk about our planet Earth, I think we should include moon in our ecosystem and look at it as such. So it will change the way we treat our resources.
So the moon and asteroids are all part of our neighborhood. We just need to expand our minds and how we think about it. That's something to look forward to. Thanks to all of our panelists for sharing their insights today, and thank you for joining us.
Hola, soy Miguel Olivares Méndez, soy profesor en robótica espacial y el jefe del grupo de robótica espacial aquí en la Universidad de Luxemburgo, y este es nuestro Luna Lab. Este laboratorio emula las condiciones visuales de la superficie de la Luna. Para ello, hemos construido una habitación cerrada de 80 metros cuadrados y la hemos rellenado con 20 toneladas de basalto. Tenemos basalto de diferente granularidad y rocas de diferente tamaño. Estas rocas representan los restos de los impactos recibidos por la Luna a lo largo de su vida por meteoritos o asteroides. Para emular la iluminación en las diferentes latitudes de la Luna, hemos instalado un foco de gran intensidad que podemos mover en altura y posición. Las zonas polares de la Luna han cobrado gran importancia gracias a los últimos programas de la ESA, la NASA y otras agencias espaciales. Eso es debido principalmente a la existencia de las regiones de sombra permanente. Diferentes investigaciones científicas han probado que en esas regiones de sombra permanente existe agua en estado sólido. La extracción de agua en la Luna es de vital importancia para las futuras misiones espaciales. De la extracción de agua en la Luna podremos desarrollar combustible para las naves espaciales y obtener oxígeno y el propio agua para el desarrollo de la vida en la Luna. El agua no es solo el único recurso importante que existe en la Luna. La robótica lunar es de gran importancia para la extracción de agua en la Luna, y es necesario que esos algoritmos sean testados antes de enviar los robots a la Luna. Y es por ello que en este laboratorio vamos a probar, evaluar y validar esos algoritmos para que se puedan enviar los robots a la Luna en un futuro próximo. La navegación autónoma en la superficie lunar presenta grandes desafíos que son similares a los que se pueden presentar en la superficie de asteroides. En un futuro, no solo seremos capaces de extraer recursos espaciales en la Luna, sino también en asteroides, aquí en la Universidad de Luxemburgo, en algoritmos que nos permitan la navegación autónoma robusta de robots para la exploración y la extracción de recursos espaciales.
And that's it. Asteroid Day Live 2021 is drawing to a close. What an extraordinary universe we live in, and how lucky to be alive when so much fascinating research is taking place. We hope that we've been able to convene the dedication and the passion that these researchers and engineers have for their subject. Thank you again to our sponsors, Broadcasting Centre Europe, SES, the B612 Foundation, the Luxembourg Chamber of Commerce and the Luxembourg Space Agency. And thank you to this year's partners, the Association of Space Explorers, the Planetary Society and the European Space Agency, and Twitch TV. Lastly, our biggest thanks goes to you, our viewers, and to the tireless army of volunteers who have organised thousands of independent Asteroid Day events around the world over the years. Together, there have been Asteroid Day events in 125 of the world's 195 countries. This is a stunning achievement, and we thank each and every one of you for your efforts. Remember to visit asteroidday.org for the latest news and updates, and we'll see you all next year. I'm Lisa Burke. Thanks for watching. Happy Asteroid Day!